So, now to the last talk. And this is less mathematical, this one. It's more conceptual. And it's based on the joint work with Jim Ramsey from McGill University. And it's based on a paper which has appeared in JASA 1 year ago. Okay, it's combining registration and fitting with functional models. And so it's on what is sometimes called in functional data analysis, the registration problem. And this registration problem is, for many data set, is very important. But at the moment it's, I think, something that's not really very well analyzed. And there are many papers on that, but usually people just present some algorithms without giving properties and show that it gives some nice fits, it looks nice in the end. So in this paper what we tried a little bit to consider this problem from a conceptual point of view, so that you can perhaps later on consider it in more depth. This certainly doesn't solve all problems you may have in this context. So here let's just assume that I have some smooth random functions, no matter how they are generated. So maybe you directly observe functions, or you get it just by some smoothing procedure, right? I don't care for estimation error or something like that at the moment. Just say, well, we're given some random functions. I want to analyze them. So, okay, and they are defined on a fixed interval, which is, say, just 0, 1. Now what you observe, from many samples in practice, is that the functions, you see, possess some common characteristics. The functions share a common set of shape features. Shape features of the function, that is the idea, for example, peaks and valleys. Just the maximum, minimum, and so on. And in many cases, I know, if you have samples of curves, for example, I don't know, growth curves or something like that, these features are very similar from one curve to another. And the sizes, for example, of peaks and valleys, they may vary. One may have, if there's a particular peak, it may be higher for one individual, for one curve, than for another. And we refer to this as amplitude variation. But also, and that's what is called, what leads to this registration problem, the location of features may vary from curve to curve. In the growth curve you may find a certain peak at a certain time, and in the second curve at another time. And so in a way for curves you have something like variation in this amplitude, in this vertical direction, that peaks are different in height, for example, but you also that they are shifted in a horizontal direction, that they are vary in location. And the presence of phase variation poses problems for the computation of pointwise mean variance correlations and everything that's usually done. For example, principal components, but also the mean. Already the mean is a problem. This is, I think, perhaps best illustrated by some examples. So this is nothing serious, this is just a simulated data set. But it represents some features you often have. For example, what you have here, you have a bunch of curves. And in a way the structure of these curves is very similar from one curve to the other. You always have something like goes up, there's a peak, goes down, and then there's the next peak. You know, so essentially you have two maxima here and one minima there. But you see, well, okay, you have variation in this direction. The height of these peaks is very different. But also you see, for example, this curve, this peak is located there, for this curve it's located there, and so on. So we have something like a variation in a vertical direction, but also in horizontal direction. There's also variation from curve to curve. And this thing poses some problem. And for example, if you, for that, one of the important things is functions of principal components. For this type of curve, they explain 85% of variance. And now the idea is what is called registration procedures, registration procedures, try to eliminate this horizontal variation. Tries to align curves so that the locations of different features is about the same. This is, for example, something like a line curve, registered curves. For example, there you see, okay, there's still variation in this vertical direction, amplitude variation, but for example, these peaks are quite well aligned. And for example, in this case, something for this registered sample, the principal components account for 100% of the variance. They're just generated, the two principal components which are shifted in time. Registration is usually done by applying, say, by considering xe of h of I, where h of I is a warping function that makes a time transformation, so to say. And the major problem is to determine this h of I. Just to show you some other examples, for example, these are some real data problems. The copy is not quite good because this is real data we used in papers 15 years ago, and I've lost the original PDF file, so these are just scanned from the articles we wrote in this overall. So there you see it's not a very nice quality, just because in one of my moves I lost these PDF files concerning this type of data. For example, what you see here is visually evoked brain potentials. This is an EEG analysis where you consider these electrodes of the brain, yeah? And visually evoked means there's a flash of light, and they consider then what the brain potentials arise in this context. And these visually evoked brain potentials usually have such a structure. For example, you see in this curve here, goes up, there's a peak, goes down, another one, and there's still another one. So in a way, you have this typical structure, more or less in all of these curves. They are not really very smooth very well, so there are maybe additional wiggles, but you see this typical structure everywhere. And for example, these peaks here and these locations also have names. And by the doctors, they try to interpret that. They have particular names, and they try to interpret these names. But what you also see, for example, okay, what is here, this is just a stack plot, so we've added a constant to each curve so that you're a little bit one above the other. Okay, that is, but nevertheless, what the peaks are, for example, this structure here is realized with different amplitudes, depends on the individual, how high this peak is. But also you see, for example, this is much earlier here than there, or than there. And the second peak also here is quite late, here it's much earlier, here it's much earlier, and so on. So there's variation in the vertical direction and in the horizontal direction. Okay? And for example, what you see here is a little bit, what is the problem if you have this variation in horizontal direction? I mean, just consider two curves. Just consider very simple. Bell-shaped, one is like that, the other one is like that. Okay? Okay, no. Let's make this smaller. Okay, the other one is like that. None of the same structure. Well, the problem, for example, if you want to determine the mean for that. The mean of these two functions, well, how it would look like? Oh, I don't know exactly. Maybe something like that. Maybe something like that. The point is that, for example, here each curve here has the same structure, but you have different locations where you find corresponding elements of the structure, and if you at the average, well, all this will be smeared.
Well done.
Well, it's true, huh? So all this structure will be smeared. And if you have a third one, which is, for example, there, average of these three curves will result in a curve which has nothing to do with the structure of either one of the individual curves. Okay? And so essentially, if you take your mean, well, it doesn't represent anything really. Right? And so the idea is, in a way, this kills you, this effect. If you do want to do reasonable analysis. Also, if you calculate principal components for things like that, whoa, okay, theoretically, if you have enough principal components, if you use, you have many more curves of that, and you use 20 principal components, maybe, okay, maybe an appropriate fit, but there will be nothing interpretable will happen. And even the mean will represent nothing. And so the idea is, well, this is a problem of this horizontal variation of the common features, and you want to align the curves in a way that something like they are now on the same scale. Then you can average. Then you can compute principal components. So that's the point. And for example, what you see here, that was an application. This is, for example, a result for this. This is here the dotted line is just what you obtain as a mean curve if you average over everything. Yeah, just a pointwise average, time by time, for our curves. And what you see is exactly this effect. I told you it will be smeared. So this thing doesn't really show any much structure anymore. Whereas these are based the means of curves after you have, in a way, registered the curve. That means you have a little bit tried to eliminate this phase variation. And there you see much more of this typical structure. Okay? Okay, this was interesting because it was an analysis, what's the difference between normal and mentally retarded children. See, the difference here is much clearly visible. Or another example. These are human growth curves. So it's based on data where they have measured the growth of children over 20 years in Zurich. Yeah, so just from birth to the age of 20. So they have half-yearly measurements of the height. Usually the growth curve itself is not so interesting, it's just going up. Except, the only exception I've ever seen were some children with some renal disease who actually shrunk. So that was really, that's poor children. No? But nevertheless, what you're more interested in is growth velocity and acceleration. Perhaps acceleration is even more important. And there you see some typical structure of these peaks. For example, growth velocity. Yeah, so where you grow. Again, this is a stack plot, so we have added constants in order to that this represents and not gives just so that every curve is well represented and not just one bunch of lines. So these are girls, these are boys. Okay. And so what you see, the typical structure of this growth acceleration curve, of the growth velocity curves, is that growth velocity drops off after birth. So you grow rapidly just after birth. Everybody who's ever had a child knows that. So in the first year you grow rapidly, and then the growth velocity goes down. There's something a little bit, again, a little peak there in the growth velocity around age 5 or 6, which is called the so-called mid-growth spurt. And then the growth velocity goes down again a bit until the start of puberty. So puberty, there's the growth velocity starts again. Yeah, so you grow faster in puberty than before. So, and this is the pubertal growth speed. Yes, and what you see here, of course, now how big this pubertal growth peak, for example, is depends on the child. It's different, individually different, but also childs get into puberty at different times. Some enter puberty at 10 or 12, and some are very late and don't enter puberty until 15. That also happens. And so what you see, for example, if you consider these boys, this is one with an early puberty, with this pubertal peak, and the growth velocity is very high, it's very early, and this one is quite late. So you have a lot of variation in this sense. And this also has a substantial interpretation. And after puberty is finished, growth is finished. Yeah? Then you start shrinking a little bit for the rest of your life. You do. Okay? And you also see there's a difference between girls and boys. You also know girls usually have an earlier puberty than boys. But to analyze these curves, even to get the mean growth curve, Well, if you just, for mean velocity curve, if you just average all these curves, well, just for example, this Bob-Brattle thing will be completely smear. Because you average over regions which are not really comparing. For example, if you split here at 12 years and average everybody at age 12, well, some of the boys already are in puberty, go to the Bob-Brattle peak, some have not even started. So you don't average over comparable regions, and this will be just some flat thing. And can't forget about principal components, even the mean doesn't represent anything. So this is a little bit what comes out after alignment, just to see what's the difference between girls and boys who become tall and small adults. And the result indicate that it's mainly due to pre-pubertal growth. There's a difference.
So this is the average without registration?
This is the average after registration. It's average after registration, and it's just because I don't show here, I haven't found any plot, the average without registration. We did not, everybody in medicine knows. This was a paper published in the Annals of Human Biology, and there everybody knows about this problem. It's not necessary to illustrate that. No, this was just more, it was registered curve, but of two different groups. These are the boys, the solid lines are boys who become tall adults. You know, we have just made two groups of the boys, tall adults, small adults. Yeah? And these are the average curves for boys, for the group of boys who become tall adults, the average growth velocity curves, and these are the average growth velocity curves for boys who become small adults. And you see the main difference was pre-pubertal. You have a smaller pre-pubertal growth velocity. Okay? Okay, but so these are some examples. But now let's consider this registration problem more generally. The point is, what you will want to do for these curves is, well, before you do any mean, before you do any type of principal component, see how it happens, you have to, in a way, to get rid of this horizontal variation, or to get it out. And the point is, there is no easy model to describe that. It's not just some fixed shift or so. Yeah, it's some time variation, which maybe continues some time. You don't know how it looks like. Okay, and so the general problem is you search for a smooth, strictly monotonic transformation H associated with a given x, called it warping function, such that the functions after this warping that we could consider x of h of t, which makes all the differences, which transforms on the same scale. Yeah, which for example here transforms everybody in the growth velocity on the same scale, so that for example puberty is at the same time. And you apply that to each curve, just to get the scale difference. So that's the usual thing, what you try to do. Determine a warping function such that after the warping, after you have applied these curves, the h's, the curves have their main features aligned. I mean, of course, sometimes there are parametric procedures, parametric warping functions. You say h of t is something like just a shift, say t minus theta. Yeah, it would be just a time shift, right? Or you may say it's not on the, or that would be parametric one, where you just have one parameter. Or you might say, oh, the scale is different, and so on. But in more complex problems, and for example for the growth data that's the case, that's not okay, it's not a simple shift. And so you have a non-parametric problem, you have to determine this h as non-parametric. Okay? And say, usually, the problem is what's your criteria of success? When did you do good registration? Well, the usual criteria is more or less just a visual one. They look well aligned after you've done that. Yeah? And there's no longer a lot of phase variation. So, for example, what you have is landmark features. Landmark features are these features, for example, as the peak and values, that we call landmark features. Yeah, so something you see, you can determine from a curve. Or other approaches, for example, functional principal components, we consider as more complex type of features. So that you may also say, well, my criterion of success is that after alignment, everything should be nicely described by a few functional principal components. Okay. Just to give you another example of such a warping procedure. For example, this is what's the pinch force diagram, Rams and Silverman found it in their book about functional data analysis. The pinch force, it was just something they had to press and exercise a force on a certain ground. So the people got the signal and they had to press hard, as hard as they could. And then let go. And what you see here are the original curves, just a little bit interpolated, not really smooth. What you see here, well, you see it's always like that. The people start pressing, they press harder, and then they release. So it's something like a curve that always goes, the force goes like that. Okay? But of course what you see here, that was a signal, and people have different reaction times. So the pressing starts early for some, quick reaction, and some didn't pay attention and started very late. Okay? So all these curves have the same type of structure, but it's exactly, you're exactly in this world. It's very simple curves, but they are at very different locations. And the idea is now to get rid of this variation here, because if you do average of that, it will have nothing to do with an individual curve. And so the idea is registration warps everything to the same time scale, so you end up with something like that, where the peaks are at the same time. Right? And that's of course, so that's this registration problem, how it is usually seen and how people usually write. Not really a criteria in a sense, that you try to optimize something or so. It's more, the success criterion was always you come from this to that. So it was more visual. And it's essentially...
One more question. So you just not only move, just somehow scale this curves? Or?
Well, I move it just by, you have a time transformation. Yeah? Okay, so you have an H. The idea is, for example, you have a fixed interval. What we have here, say 0, 1. The H now, just to be simple, we have, it's just a mapping. The H of t, that is the mapping from 0, 1 to 0, 1. Now, no warping at all, and here you have the time. The time. No warping at all would mean you are the diagonal, would be ht of t. ht of t. No warping at all. Yeah, so we have what you do to determine the warping function to go from this to that. So for each curve here, you apply such a function h of t with the idea to have all features aligned, to change the scale. If the function h of t is t, that means just this diagonal here, no warping. So we don't change anything. Then h of t is x of t. Now, of course, the h of t may be something like that, for example. Okay, this may be h of t. Okay. What happens with this h of t? What happens to that? What's the difference between x of t and xh of t? Well, it means, for example, if you here have the point, I don't know, 0.4. So, and here it's 0.4. You see, for example, then h of t will be already perhaps, I don't know, 0.6. Okay? So it warps one time from the time 0.4. It's something like, you're already now at the point 0.6. And this corresponds to the thing that, for example, in order to have to have the same scale, you have to shift that. You have to make here, because this is very early, everything a little bit later. Later would of course mean inverse thing. And for this thing, everything has to be a little bit earlier. So this would mean, for example, a warping function that's like that. Okay, and 0.4 is only 0.3. So it's a little bit of time transformation. Yeah, you change the time scale, and if you have in a non-parametric world where you say the HD are not simple shifts or something, because you see that doesn't work, they're just some functions here of time. And of course, it's also possible that somebody may be early at the beginning and late at the end. Then you would have a warping function that crosses the diagonal somewhere.
So if I have functions that are like this, increasing first and decreasing, if I choose suitably my age, I can warp them all to an arbitrary function like this, and then.
Right. I mean, you could say, of course, the warping has to do. In order to have a warping procedure, you have to have a common scale at the end. This common scale can be the scale of one individual. Say, that's my basic individual I take, and I want it at the scale of this individual. Yeah? This means you take one curve out and warp everything to the scale of this curve. Or you could say it's something like a mean scale. That means an average scale of everybody. That's the usual thing what is done. So that you say we want, for example, that all features, for example, everybody has this peak aligned. Yeah. So the differences in location of these peaks are eliminated by this warping. But the peak should, in this curve, appear at an average location for all curves. Yeah. This would be a mean scale. I mean, in principle, the scale is something you're free in choosing. You can take an individual scale or the mean scale. So usually what people do is they want, for example, in this case, that after warping, for example, this peak are well aligned, take place at the same time, but this time is the average time for all this. Yeah, you can, of course, for each peak you see that's time, this is this time, and there's an average time. This would be something people would like to do. Well, what we try to do usually, as I said, most papers in this direction, they such say, I have here an algorithm, apply it, and you get that. You get this thing, and that's a success criterion. But first of all, just to understand what's the underlying problem, in a way. Why to apply this procedure, and what are we trying to do? So what we say here a little bit that what's the underlying problem? Why is it difficult to work with these things? And well, the point is a little bit from a mathematical point of view. That's not very difficult to say. We say all curves have they take a space in a certain function space. For example, a function space of all bell-shaped curves, which start from 0, have a peak, and start 0 again. Yeah? All curves you observe have this structure. So this is essentially a function space, and this may result, this may result, this may result. And for example, if you say this is all this the function space of what bell-shaped curves. Well, by bell shape I mean this thing. Okay. The problem is, mathematically speaking, this is a space which is not closed in the linear operations, which is not a convex space. Convex space means the problem is if you have two curves of this type, if we average them, the average curve will usually be not of that type. Yeah? If you average two bell-shaped curves with different locations of this peak, then the average will not be a bell-shaped curve. So the average will not represent the typical structure. So it's not a convex space. And in a way, in statistics, we always have problems if spaces where we consider not convex. Yeah? So essentially, that's the major underlying problem. Then means doesn't really work. Also with the variance you have problems, principal components you have problems, and so on. Okay? And the idea is, well, to remove that. So the warping have to be defined in such a way that the space of the registered functions, which you call the synchronized space, S, that is a convex space. Then you can do average. And for example, with the alignment, this works. Because if, for example, if you say bell-shaped curves with a peak at the same time point, if you average these curves, it would be a bell-shaped curve. just because you always have the maximum at the same time. So the average of this thing will have the same property, if they are aligned. Yeah?
But the average of the smoother functions will be smoother functions.
Yes, but they will not have this structure. That's the point.
But then the originals are subspace.
Yeah, it's a subspace. That's what we will want to say. For example, I meant more specific spaces. For example, space of bell-shaped curves, not only of smooth functions. Okay? Of course, if you're in L2 also, that's a convex space, but this doesn't capture all the properties you have. The properties you have in this example, it's a particular space, and this is this space here, which you have to deal with, and not just generally L2. Okay? If you, of course, you have several functions which have no common features, which are just somehow, and one function has nothing to do with the other, okay, then you're L2 and everything is okay.
Is it important to have the common domain then?
Yeah, sure. I mean, the common domain is something which it's not really important, but it simplifies life if you consider it from a general thing. So we have the same domain. Yeah.
But if the curve is shifted, I mean the common
Yeah, sure. I mean, with the shift you may get out of it. This you can treat that. It's only for this discussion. Yes, fixed domain. Okay. Also, the H is started at this end point, and the things are the same. But that's not really necessary. It only simplifies life. It's not even something you should use always. Okay? And so, in this space, if this is a convex space, then you may consider averages and also consider functional principal components. Yeah? So that's a big difference. If these peaks are not aligned, it's not a convex space. With peaks aligned, yes. Okay? Of course, the problem is, if you want to do registration, you determine for each function you observe, you have an H. And so they are different for different functions. So if you have the individual function I, you also have an HI. Which of course means that what you do, oh my god, that's not so easy, because you split one function into two components. That means into the HI and into the synchronized curve, into this registered curve. Because this is your registered curve yi. So what essentially you do is you decompose a single function into two functional components. It's a warping function and the corresponding registered. And splitting one function into two, there is usually no unique way to do so. So unless we have specific knowledge about the data generating process, and of course in this context we should use all knowledge we have, there's no unique registration procedure, and when choosing a particular method one has to focus on statistical interpretability. That's the major thing. There's no unique truth which can be identified, except if you have really knowledge how these things are generated. You need a real model for that, a substantial model. And that, apart from that, it's not really unique. There are several registration procedures which may be used. And the important thing that you can interpret it on a statistical level what comes out. So for the same space X, different forms of registration may lead to different warping functions in different synchronized spaces. I'll give you an example. This is example of space of this type of bell-shaped curves. Yeah? I made this thing a little bit more extreme than in this real example. You see every curve here starts at 0, has a peak, goes down. So that's the common characteristics. All the peaks have very different amplitudes, and also see locations are extremely different. Again, if you take just the mean of this sample, it will be something catastrophic. It will not represent anything. Okay? So you want to align that. Eliminate these differences. Get to the register space. And for example, there are two simple approaches you may use. One is, you just say, well, I want to align peaks. So what I could do is very simple. I could say, well, this curve has a peak there, this curve has a peak there. So the warping must be done so that the HIFT, the peak locations are all at the same point. Okay? I don't know anything else, so I only have information about the warping function at one point, the peak location, and I just interpolate between. For example, linear interpolation. So I just use a piecewise interpolate the function, starts at 0, starts at 1, and we have common location tau, where all the peaks at the end should be, and I assign it to tau, the tau x location of the peak for the particular curve. So that's one way. That's what's called landmark registration. Just use this peak landmark and interpolate in between. But there's also a second way to do that. For example, you may say, okay, all these curves, if for example you have something like these curves, essentially the registered function should only essentially differ by some amplitude. It's something like if you multiply this by a certain amplitude so that they have the same value, essentially you would have the same functions. So what you could say, you choose a template function, say one of these functions, mean function would be some typical function, and we align everything to this function. And we say just you choose a template function, and let the synchronized space be the space of all functions which are just an amplitude, and parameter theta times these amplitude functions. Yeah? So if I choose this as amplitude functions, then for example the theta is just a parameter that brings this height to this height, and who brings this height to this height to this height. So that's another way, and I just then use a registration that after eliminating these amplitude differences, the curves are identical. This is also a sensible registration procedure, and for example, these are the results for this data I showed you of these two different procedures. This is this landmark registration. These are the edges that result. I just align the peaks and interpolate, make straight lines for the edges. And from that, and these are the registered curves then. You see, they all have the peaks at the same time. This is what is resulting from this template registration. I choose one curve and register in such a way that there's only everything is equal up to one amplitude parameter. And then I get these registered curves, which look much nicer than that. But at the cost of, you see here, these are more complicated warping functions, which are determined automatically in this case. It just warped that there's no difference left. Okay? And of course you may go on further with these things. So you have something like a simple template function that you say, well, essentially, for example, this type of curves may be in a way well represented, but I think there's one basic underlying curve, which I call theta, which has this structure, and all the others in a way I can generate by warping from these basic functions and by adding an amplitude shift. So in a way, all the curves I can observe, can say, well, there is a basic bell-shaped functions, and all the curves I get is something like that xi is something like a parameter theta I, that is different heights, times this ci, times this c of an inverse warping function. It's just a time scale of warping. That's okay for this type of data. You could say that. You can generate it in that way. And then you can, in principle, there are procedures to determine this theta and corresponding warping functions. There's what is unclear still some scaling, but you can always normalize it the way you consider different warping functions here. Each xi has a warping function hi, and the scale, as I said, is in principle something you can choose because it only fixes the scale of theta, which is arbitrary, and you can always choose the scale such that the scale is standardized in the sense that the expectation, the mean, the h is as just this diagonal, HIST. That's no restriction, it's something you can always do. It's just choosing the scale to be the mean scale. Okay? And then you can show the components here identifiable. The problem is this way doesn't really work well for more complex curves, this works with one peak and so on. But for example, in the other example where we have these two components, which also differ in their amplitudes here, this doesn't work very well. This just doesn't describe the same. So this doesn't matter. And well, we could say, okay, we could still say something, even if it's more complicated, well, we could perhaps add something so that our original xi is just generated by some basic function which contains all the structure, and an inverse warping function. You see, if you multiply x of h of I, this would be a way. And just say, well, now perhaps these parameters may depend on t. Just to get more complex structures, not just one fixed parameter. Unfortunately, it doesn't work because there's no way to identify these two things. So this doesn't work. This doesn't work. But what does work, for example, for these more complex structures, for example, here you may say, okay, this is one component which you have, which is different, where you have different amplitudes and which is warped. Well, and here you have two, very simply, this one and this one. And so you may just say, well, that the space is such that after registration you have something like superposition of two components with two different amplitudes. So one component here, which has its proper amplitude, one component here, which has its proper amplitude. And this is something that's okay, that works in this sense. So there are several template functions in a way which correspond to different functional components. So, say, this obviously has to do with functional principal components. Okay? Now, okay, but the first thing is, of course, as I told you already, there's no unique registration. There are always different ways to do that. For example, as I said, you could do it like that, you could do it like that. The main thing is statistical interpretability, what you prefer. This depends on the application. But nevertheless, aren't there any type of assumptions you have to do in order to get a sensible registration? Well, usually, as I told you up to now, people just present an algorithm without trying to develop at least some type of theoretical framework. And, well, I think that nevertheless there are some features a registration procedure should have in order to be statistically interpretable, in order to be reasonable. This is not unique, but anything, and this property which we require is called consistency of registration procedure. Consistency doesn't have anything to do with stochastic convergence in this case. It just means an internal consistency of the procedure, that it doesn't really do as it will. So the first thing is, of course, what I already said. You start with such a space which is not convex, and you want that the registered curve, the space of registered curve, is convex, so that you can really work with usual taking means and so on. So that's the first thing. But it doesn't quite suffice. It's also, what it does, any registration procedure makes a difference between phase variation, which is eliminated, and the remaining amplitude variation, which is in the registered curve, for example, and described by amplitude parameters. And nevertheless, there's no unique way to do this decomposition, but nevertheless, a registration procedure should have an idea what is phase variation and what is amplitude variation. And so it should not be an arbitrary assignment. And so what we require here in a way that a registration procedure should be such that already, if you have already registered a curve, yeah? So if you have a curve and have defined a warping function, and then you input this yi into this procedure again, then it shouldn't change. So you should say that the registration procedure should be clever enough to say, oh, this is already registered. Nothing should be done anymore to that. Okay? So that's the second. So the registration of functions that are already registered does not transform the argument. Yeah? But in principle, it's a measurement that aligns every curve of this type from the basic structure, we suppose, gives a warping function. But I think these two these two properties should at least be satisfied in order that a registration procedure makes sense. And these are not simple properties. Not very simple, not very simple to show that. We can also say from the standard, what I call a standardized registration procedure, that's something where the basic scale where you walk to is just a mean scale. So that, which means that you require that if you have a sample, that the mean of the ages is just the identity function. This means that you have a mean scale. This would also help that, for example, if you align peaks, the point, the time point where it is aligned is just the average location of these peaks for all the curves. This makes a lot of sense. It's not necessary, you can do it, if you want to do it, you can do it differently, but this is no restriction. And what we call the structural mean is just now the mean of the registered curves. This is called nu, and mu is the mean of the original curves. Okay? So this is the thing. And for example, one consistent procedure is landmark registration, which we already knew, which, for example, if you have a number of landmarks, these peaks and valleys, give you here an example where, for example, here you have always this peak, this valley, this peak. It tends then to align these things by transforming the curve such that these peaks are the same points, this valley is at the same points, this peak is at the same points, and in between these points it just interpolates. That's landmark registration. And that is a procedure that is consistent. You can show that it satisfies our requirements. So this procedure is consistent provided that the interpolation scheme is such that HT is T for all T, and the registration process is well controlled and statistically interpretable. It may not necessarily be what you want, but it's interpretable. And warping functions are parametric functions. Disadvantages is that the selection here of an interpolation scheme between the peaks, between the valleys, adds a subjective element, and different types of interpolation lead to different registration procedures and may produce different statistical results. And also, it's usually in many cases in practice you have to estimate curves, and they may be not clear or unique due to over smoothing, or so you may have too many peaks. Yeah, just have random peaks, and so it's a hard business sometimes to identify corresponding features. We did it a lot of time ago for this growth data I showed you using landmark registration with the Burdle peak, the mid-growth spurt, and then it wasn't so simple. For example, I did a graphical program where for each curve you could manually select the corresponding peaks. Yeah? And so it was something like 400 growth curves, and for each curve, together with my boss at that time, we sat there and made a manual landmark registration. Well, just from estimated curves, it's not always simple. Yeah? Because peaks may be suppressed or additional peaks may be there. Another very popular one, which is still not used in practice, in particular what is a big problem, here I consider one-dimensional registration, but the big problem in medicine is two-dimensional registration, for example, of brain images. If you have brain images, for example, very usually there's one picture, and for example, a minute later the next picture, but the guy has moved a little bit. So the pictures are just a variation in shape. And so there, for example, all these registration things are very important. They are basic things just done before interpreting brain images. Huh? Yeah, that's two-dimensional, but essentially what I say here also applies. Huh?
The brain is three-dimensional.
Yes, but the pictures are two-dimensional. No, they are two-dimensional. Okay, the third is usually, it depends on the pictures you take. Okay. Okay, your pictures are three, okay. You are more advanced than the doctors, okay. You know, some doctors also have three-dimensional, but okay. What this is done is very simple. You choose one template function. So one function, typical function out of the sample. Which one is not easy. Sometimes this is done by iterative procedure. Choose one and later on you improve. And then this defines then your basic time scale. Yeah? This one particular one. You take this one. Okay? And then you define a warping function in such a sense that the difference between the registered curve of h of t and this template is as small as possible. Unfortunately, this does not work very well. Why? Okay, but see the temporal function can be defined iteratively, starting with correct sectional mean of x. In each iteration, new mean of the previously registered curves is calculated and functions are re-registered. So it's not necessary to take one individual. Sometimes this is done. But let's stick to the thing. We have one curve, for example, this one, okay, where we want to align. The problem is this square estimation is only consistent when no amplitude variation is present, so that all curves are just have here the same height, which is in practice never the case. But if there's amplitude variation, there's a problem which is called, Jim Ramsey has called the pinching problem. There's a tendency towards extreme deformations, a walking function which has jumps or which have constant segments. Why? Well, it's very easy to see. For example, if you want to align this red curve to the blue one. The problem is there is no way to define a warping function that really makes this difference small, just because the peak here is much smaller than the peak there. No way. But what's the best selection of a warping function? Well, okay, very simple. The first, until this height is reached, you can very simply just transform this one so that it matches exactly this form here. But then you have a problem, because you can't go any higher than that, the warping function. Yeah? As you see, the maximum here doesn't depend on h, it's always the maximum of x. So what does it do? Oh, it adds a constant segment, the warping function, so that a lot of time the registered curve this peak here is just expanded, the peak height. So just this small region around the peak is expanded enormously, which means that you have something like a constant h. And then it goes down. And obviously would say, well, this isn't a really nice type of registration. It would be extreme warping. So usually this thing leads to warping functions which either look, for example, are like that, okay, or are like that. There's a jump somewhere. Okay, so and that's not the idea. It doesn't really work. That's just the underlying problem is that just the least square is questionable, because a correct, a nice alignment will nevertheless not make this difference extremely small. Yeah.
You can always normalize it just by dividing the maximum. So that
Well, this may work for if you have things like that. It doesn't work for more complex things. There are ways to. I don't say that that there are no ways to do it. Yeah, it's only this method doesn't work. Okay, and the underlying problem that in the presence of amplitude variation, already this difference may be large if x is properly exposed. What people do, and that's always that's also what the doctors do when they register brain images, they add something like a penalty. For example, they say h's, we only choose h's which are twice differentiable, and we add a penalty that the integral of h squared, the second derivative of h, is smaller than some constant c. This, of course, avoids things like that, because there the second derivatives will be very high. But the problem is, if you do that, this method is not consistent anymore. Because what will you do? If you add such a constraint, then, okay, it will. The least square registration will go into this direction as far as it is possible, until this, so that the constraint is still satisfied. Okay. But for example, if then you have a warping function, if this thing you apply this procedure again to this registered curve, it will go further into this direction. If we try to go further to this extreme way. Yeah, you can just by adding this constraint, you can say, okay, this is not possible. You end with a quite smooth function, but if you apply the procedure again, is a new constraint, and it will go further into that direction. So it will not be consistent in the sense that it has no idea what is amplitude. It tries to explain everything by amplitude, by phase variation, and this doesn't work. Okay, so.
Okay?
And some outlook.
Okay. Okay. Then explain the active variation by principal components. So what we did a little bit was the idea that you have these spaces here with the different components, but you may have not one, but several. So in order to be able to explain curve samples with more complex structures. And of course what you could do is that you could try to do decomposition of the registered curves, the types of functional components. Then you have something like eigenvalues and functions composed from covariance y, and then you get, of course, something like mu IP, that's an approximation of your existence by E principal components. And there's, of course, something like what is the rest. And we all know this is in a way, if you are looking for different components, just an approximate function by a small number of basis functions, principal components are best choice. That's the reason why we try to use principal components. And there you get also an alternative variance decomposition. And here this part, the amplitude variation, the resistance curve, you can of course decompose also in the part explained by the first big principal component. And the part which is obscured after the people. So that's the whole. And you can then say that the total variance of your sample is the amplitude variance explained by the principal component, phase variation explained by walking functions, and that of rest works out. And what you can show, whereas functional principal components of the original random function not do that here, just because of as already. We have a small theorem, in a way, which says that if you have random functions, which have at most a number of features, we call here just speaks and value things. So if there's samples of the probability 1, yeah, at most number k of features to be found in every sample. For example, in this type of sample, you would only have one of these features. In others may have 2, in others may have 3. Then you can always say that there is some p, as equal to k plus 2, that there exists some smooth functions you want to see, such that every curve can be, in your sample, can be generated by a linear combination of these p basis functions together with some walk. G is just inverse walking function. Well, you apply something like this H to the minus 1. So every curve sample with limited number of features can be explained like this. And then you can from this define a consistent rate distribution procedure that for any x, the walking function R is the element of H, which is the smallest value, where this is a set of all H satisfying that it is well explained by this the registered function is well explained just by a linear combination of these basis functions. And of course, these basis functions you can identify them with the eigenfunctions of the covariance operator of the registered curves. So you can conclude that for any sample of curves with a limited number of features that you observe, there exists a procedure that the registered function can be written in the following way: that it's just a linear combination of p basis functions, which can be identified with principal components, because principal components will give you the sparsity distribution. This is easily shown. And so this space here is necessary also space spanned by the first principal components, just to do that basic problem. Yeah?
Why didn't you consider registration for the income distribution?
For the income distribution? Well, because after our mean scaling,
it's automatically
the registration
registered.
there was no registration problem anyway.
But the peak was...
If you don't do our mean scaling for these things, then you are lost. Then you have to. But this mean scaling in this case was registration.
Yeah, the whole thing was that the peak, one peak went down, other peak went up, but that's exactly what you would like to see after registration, because that has an economic interpretation.
Okay. So, the idea is that this in principle provides a generally applicable decomposition of variance of curve samples into amplitude moderation, modeled by principal components, variations of curves, and phase formation, modeled by walking functions. And so the idea is here of our registration procedure is just to determine walking functions HI such that, well, the resulting such that for a given P, the registered curves have the best possible description, most precise description by P principal component. So this is criteria, so that the difference between I and its the first principal, and the approximation by the first P principal component is made. So we determine at the same time is theta, the nu, and H, just by trying to get the smallest differences. The best, we try to find a registration procedure, the HIs, such that after registration, the registered curves are described by the least possible amount of basis functions, least possible principal components. Here's a description of the algorithm, which now I don't think I have a lot of time to discuss in detail. Additionally, there are some of my people working on that. It doesn't work too well. I must say, unfortunately, there is some different have to be done in this context. I'll just show you perhaps one application we tend to stop a little bit. There is something like application to handwriting data. There are 50 samples of the production of the Chinese script for statistical science. So I think somebody can read Chinese here. So observation consists of the position of the infrared detector, 25 attention to the tip of the pen recorded 400 times per second of the motion capture system. So to the pen that we wrote, there was some register was registered. So every movement was registered. And the objective was information how the brain's motor control center controls complex movement falling rapidly in time. So it's essentially the interest was in the pen acceleration. And that acceleration was in tangential space because it's a plane, so you can have something acceleration this direction or this direction. And so it was something like the natural pantic acceleration. This is X direction, this is Y direction. Okay? And just to see how this evolves. And there was some smoothing done, and we get out after our procedure that something like 30% of the total variance of the exodus could be explained by phase variation. Just to show you what happens a little bit in this context. This is supposed to be the Chinese script of statistical science with some additional riddles here which have nothing to do with it. I hope it's correct.
Is this Chinese? I don't think so.
Yeah.
What does it say?
Statistical science. I can't guarantee it.
So this means statistical science in Chinese. 3 symbols, yeah?
Yes. Yeah. It's a little bit because it added this small columns here, which are just which are not there.
Very interesting.
So what you see here is a little bit over seconds. This curve here is the pen acceleration.
Very interesting
You
data.
see that's a quite complex thing. Okay. This thing here is what was initially recorded was a vertical coordinate. Vertical means that of course the pen was sometimes lifted from the sheet. Right? For example, there's a break between here and here that had to lift the pen. And so this coordinate tells you a little bit when was the break. Okay. Okay, and to bar this, of course, you have something like 50 samples. And of course, if you're writing, it's not, no sample is exactly the same. Sometimes you are, and there's variation.
50 different persons? Same person.
50 of the same person.
So what's the objective?
It was a while. The general applicator says it's very interesting to the psychologists. Jim's a psychologist, so I hope it's true. It's an explanation, but perhaps it was only his fault.
Some kind of...
And at least he always says, this is very interesting also, because some of these accelerations are so strong, it's only milliseconds. But if you could sustain this acceleration for 2 minutes, it will put you in orbit. Okay, that you have 50 samples of the same person. Oh. And these are the 50 samples just plotted one over the other. So what you see, of course, there's the same structure, always. But of course, the amplitudes are a bit different. You know, sometimes a little bit faster. And also timing is different. That's also good. You start something a little bit later, a little bit longer. So you have both variation, phase variation, and amplitude variation. And these are called experts. They have a lot of these landmarks. And what we first did is apply a landmark registration. And the landmarks, in this case, when I just locate the peaks and valleys, this is impossible in this context, too many. But where this location of these things, when the pen was lifted off the sheet, that was used as a landmark. These were a lot. And you see, at least visually, it looks a little bit less chaotic than this. This chaos here is just, that's the same structure, but it's there's always different timing, and so what results is black. Okay. And now this is our procedure with the principal components, where we register to 3 principal components with p equals to 3. We don't start from scratch. We start with a landmark registration and try to improve it to get better registration with respect to principal components. And you see at least visually, it gives a better picture than that. You now see a little bit more that the structure seems to be fairly aligned, and there's not too much phase variation. Okay, so thank you.